QUALIFORMAT proposes two modules to control multi-leaf collimators. The first is used to control MLCs in static mode. In other words, when the MLC is used to delimitate the irradiation field. The second module, MLCdyn, for quality control of multi-leaf collimators in dynamic mode. In other words, when the MLC is also used to modulate the intensity of the beam. This MLCdyn module can be used to perform tests in VMAT, in dynamic IMRT, including step and shoot mode. I will now import a second example from Electa. This gives us two examples, one each for Varian and Electa. For MLCdyn module, it is indispensable to have our OTP Abacus test object. I will now show you. You see its version for Electa Linux, adapted for the shadow tray. We have another version adapted for the tray closest to the source on Varian Linux. The Abacus test object is a plate with embedded tungsten balls, which provide on images a reference point coming from the X-ray source. It is not used during tests, but only during the pre-test, whose purpose will be explained later on. If you want also to automate the QUALIMAGIQ test by Anne Van Esch, you need a second test object, our OTP ISO test object, normally dedicated for ISO center tests. We will come back to further on in the demo to see what is the QUALIMAGIQ test. So we need two QUALIFORMAT test objects for the MLC module. Abacus is indispensable and ISO is optional. The two exams are now on the welcome screen. The first from a Varian Italian center and the second from a Electa Belgium center. We will start with the Varian example. What is of interest to us is to enter the step-by-step mode to take an in-depth look at the test. Of course, in routine mode you use the analysis button, but for now I would like to explain in detail how the module works. So I enter the step-by-step mode. As administrator, I have all user rights to the program. To begin, I would like to describe the acquired images before we take a close look at the test. So I will not examine these first images of a pre-test, whose purpose I will explain later on, but rather will review the test images. The first test is a sliding window test, which includes a set of 4 images acquired with the 4 cardinal gantry angles, 90 degrees, 0 degrees, 270 and 180 degrees. For each image, the field is provided by a 1 mm width slit, which slides at constant speed from one side of the field over to the other side. The same dose is prescribed at all 4 gantry angles. You are aware that at 90 degrees, where the MLC needs to go up, and at 270 degrees where the MLC must go down, given that it is much easier for the MLC to go down than to go up. If the MLC speeds up as it goes down, the dose will decrease with the increased speed of the MLC, and you have prescribed the same dose for each radiation field. This test will consist in verifying that the LINAC correctly controls the MLC speed and is not impacted by gravity. The second test is named the picket fence test and sometimes the garden fence test. It controls the accuracy of the MLC used in dynamic mode. Once again, a 1 mm width slit which moves very rapidly, stopping 10 times to deliver dose. This test is carried out in static mode at 4 cardinal gantry angle and then with a rotating gantry. As you can observe here, by comparing the last static image, gantry at 270 degrees, and the image with rotating gantry. That means the image being carried out during the entire gantry rotation. The bottom of the 10 slits is quite straight for the static gantry, whereas with the rotating gantry, the bottom of the 10 slits has a wave to it. For the rotation image, each column is acquired at a certain gantry angle, and the wave is due to the flex of the gantry. In other words, when the gantry rotates, the radiation source has a head-foot movement on the imager, which is due to the flex of the gantry when it rotates. In sum, when the head is at 0 degrees, it comes closer to you, and when the head is at 180 degrees, it moves further away from you in the treatment room. This describes a longitudinal movement of the radiation source relative to the imager. It is very important that this be corrected, which we will do with the pre-tests. The aim being to remove the impact of gantry flex from the measurements of performance of the MLC. We must, however, also take into account that the sagging of the portal imager has an impact in the right-left direction. The sagging of the portal imager in the image will blur the slits. As you can see, the slits on the left are clearer, so for the right-left this is due to the sagging of the portal imager. The impact of this sagging also needs to be removed from the results. The picket fence test with either static or rotating gantry will consist in measuring the position and the width of each radiation slit and checking it with the prescription. A total of 40 leaves and 10 slits has been tested, yielding 400 width and 400 positions, repeated for 4 images with a static gantry. Thus 3,200 results, with an additional 800 results with a rotating gantry, requiring the software analyze 4,000 results with 2 mouse clicks. The following test is exactly the same. A picket fence test with rotating gantry. However, with less slits, and as you can see, as per the prescription, the slit was shifted by 1 mm for this leaf pair. And here, the slit was widened also 1 mm for this leaf pair. The position appears to be respected to the naked eye, but we can see that the width was not doubled for this leaf pair. We are likely to encounter a width value outside of tolerance. The other 2 tests consist in controlling the severing between dose rate and the gantry speed. As you are aware, in VMAT treatment, the LINAC continually adjusts the dose rate according to gantry speed and also adjusts the dose rate according to leaf speed. 7 different gantry speeds are tested here, and each radiation band the same dose was prescribed. So when the gantry speed increases, In order to deliver the same dose in each band, there is no other solution than for the LINAC to increase the dose rate proportionally. When the gantry speed doubles, the dose rate needs to double. This is precisely what this test controls. The same goes for 4-leaf speeds. Again, with a rotating gantry. When the 4-leaf speeds increase, the dose rate needs to increase proportionally. You can see that we also acquire images with an open field. These images are used to correct the influence of the response of the portal imager. We will take signal measurements in these 4 areas of the portal imager, and it is important to deduct from the result the amount due to the response of the portal imager. So, these images with an open field, static mode, are used to correct the variation in the response of the portal imager. The final and optional test is the SNOOKER-Q test. Our ISO test object is first aligned on the lasers and then deliberately offset laterally 10 cm in table and 5 cm in table height. So the central ball of the ISO test object is no longer at the ISO center. Next, there is a sequence for the gantry and for the multi-leaf at maximum speed. When the synchronization between gantry and the multi-leaf collimator are in accordance, the central ball of our ISO test object is in the middle of the radiation slit. In this example, 4 different sequences were made of the multi-leaf and the gantry. This test of gantry and MLC precision is very pertinent, with the advantage of being very quick, so it can be performed on a daily basis. As you recall, there is a fundamental problem to correct: portal imager sagging, impacting the right-left positions of the slits. There is also gantry flex, which impacts the images head-foot longitudinally. It's crucial to deduct the impact of the imager and the gantry faults from the measurements of the MLC performance, because the amplitude of these 2 improper movements is more 5 times the tolerance of the leaf position test. We have a pretest for this purpose. It consists in attaching the previously mentioned abacus test object to the collimator exit, and in detecting the 4 external tungsten balls of the abacus in all of the images when the gantry is rotated. I will do so as I begin the first test, in which I detect the 4 balls of the abacus test object and determine the center of the abacus test object, and I will look at how the center moves in the image with different gantry angles. This test is carried out with a static gantry angle. It may take a while, as 15 images were made, taking 15 minutes. Today, this test can be saved in QUALIMAGIQ for use in the next quality control without having to repeat the pretest. In other words, reusing the pretest performed for the preceding quality control to avoid having to repeat the pretest. This is now possible, as with our experience, we now know that the imager sagging and gantry flex are relatively stable over time for your treatment machines. If you carry out the test every month, you will obtain nearly the same results, so we recommend doing it only every 6 months. The results are saved to avoid the 15 minutes it takes to perform the pretest, given that the tests which follow do not require more than 10 minutes of acquisition time. It would be shame to spend 15 minutes on the pretest and 10 minutes on the test. We have now detected the center of the cross described with the 4 external balls, and we have these 2 curves. How the center of the cross, the reference point coming from the source, moves relative to the imager, head-foot for the blue curve and right-left for the red curve. The blue curve is the gantry flex. The red curve represents the sagging of the portal imager. As you can see, the amplitude of the movement is 1 mm for the sagging of the portal imager on the red curve and is approximately twice that, 2 mm, for gantry flex. Note that in the picket fence tests with a static gantry, we look for the positions of the slits with a tolerance of 0.2 mm, with a rotating gantry 0.4 mm, so a 1 mm sagging of the portal imager is 5 times the tolerance. Therefore, this must necessarily be corrected, and we are the only ones who do so. Our competitors' software open tolerances rather than setting tests at 0.2 and 0.4 mm. They set them at 1 and 2 mm for leaf positions, and so, in fact, they never test the multi-leaf collimator, but rather the impact of the sagging of the portal imager and gantry flex on the picket fence tests. In other words, it's not very relevant. We want to really test the MLC, so we remove from the images everything that could interfere with the measurements of MLC performances. As we also measured the side of this cross, which is the reason we use a big cross, we can also measure the variation in source imager distance when the gantry rotates. It is also important to take this into consideration, as those measurements need to be made, and if the source imager distance varies with the inverse square law for distances, this has to be compensated. Furthermore, with the lateral slits, with the Thales influence, poor handling of the source imager distance can lead to incorrect slit positions, not because there is a problem with the MLC, but because the source imager distance varies during gantry rotation. Thanks to the pretest, we determine portal imager sagging, gantry flex, and the variation in source imager distance, all of which we will apply to correct all of our measurements. The situation is rather simple. You want a very precise image, given that you need to make very precise measurements with tolerances of 0.2 and 0.5 mm, and unfortunately during the photo shoot the camera moves. Given that we measured the movement of the cameras during the shoot, we will correct the images of the camera movement as we were able to measure it. As we also have the two leaf banks to the right and left of the image, we are also able to add to the pretest a test of leaf bank sagging. This test, which is not a dynamic test but rather a static test, is pretty interesting. As we can see in this image, the leaf bank sagging is 0.6 mm for the purple bank, also 0.6 mm for the blue bank. So the leaf bank has 0.6 mm of sagging. It is impossible for this clinac to have correct picket fence tests with tolerance of 0.4 mm with a rotating gantry when the leaf banks have 0.6 mm of sagging. We will examine this further with the picket fence test with a rotating gantry, which we will do after the test with a static gantry. We will observe that the impact of the sagging of leaf banks does not exist with a static gantry. Here there is no problem with the position, with a tolerance of 0.2 mm with a gantry at 90 degrees. For the 400 widths tested, you can see that problems with the width begin with the last slit, with a tolerance of 0.2 mm. Now with the gantry at 0 degrees, we again have problems, but less intense, with widths for the last slit for 0.2 mm tolerance. Slits positions are still okay. The problem with widths for the last slits begins to rectify with a gantry at 270 degrees, but comes back at gantry at 180 degrees. It's not too bad overall, with a static gantry with 0.2 mm tolerance on slit position and width. Now that we have checked with a static gantry, we will look at results with a picket fence test with a rotating gantry. As you can see, we do not analyze the image, we produce a corrected image, corrected by the inverse of the improper movement of the portal imager measured with the pretest. And as you can see in the corrected image, the bottom of the 10 slits no longer has a wave which was due to gantry flex. Each of the image columns is acquired with a certain gantry angle, and as we know the movement of the imager, we apply the columns of the image the inverse of the imager's improper movement. That is for the test of slit positions. Lots of problems after gantry 0 degrees, but no problem for the slit width. Why are there problems with the positions? As you can see on the curves, the two leaf banks show nearly the same sagging. In other words, the two curves are parallel. When we rotate the gantry, the two banks move together the same amount, so the widths remain the same, but the position is shifted. This all happens at the start when the degree of sagging varies strongly on the first slit, and then at 0 degrees, as the mechanical play on the leaf banks takes the opposite directions, and all results after 0 degrees are outside tolerance. In other words, above 0.4 mm as the gantry is rotating. This demonstrates the pertinence to complete the pretest with the measurement of the leaf bank sagging. Another point of interest is shown in the graph, which illustrates the mean of the split position deviations with the rotating gantry for all leaves. Looking at one slit, we take the mean of all the leaf positions deviations, all 40 pairs. The deviation is here, and we conduct from this measurement the amount due to the leaf bank sagging, which we have measured with the pretest. You can see that on this linac, if we had no sagging on the leaf bank, we would even be able to apply a tolerance of 0.2 mm with a rotating gantry. However, given that we have a problem of sagging of the leaf bank, which is in fact the actual situation here, not this, we observe that there are points which exceed the 0.4 degrees tolerance level after 0 degrees. There are also problems with the first slit acquired at gantry 180 degrees. We see that this curve closely approximates the leaf bank sagging curve. There is a parallel between the curve of the sagging of the leaf banks and the result of the slit positions. We have tested a total of 4,000 parameters in 10 seconds, with only 2 mouse clicks. We will now perform more simple operations with a sliding windows test. As you recall, 4 static gantry positions 90, 0, 270, 180 degrees. A slit which slides from the left of the image towards the right at constant speed, and we will measure the dose level in the radiation field according to the gantry angle. The linac controls directly the MLC speed if the variations in dose are less than 2%. The original publication by Ling recommended a global test with a ROI which includes the total field such as this, and we added an individual test for each leaf pair. Green indicates that the variations according to gantry angle are less than 2%. We see that individually and globally the tolerances are respected, meaning that the linac controls the speed of the MLC perfectly well. We will now explore the gantry speed, dose rate test, dose rate servering, with our 7 different gantry speeds for which we want the same dose in each strip. We take a global measurement of the dose value, an individual measurement for each leaf pair. We also remembered to do the same with an open field to remove from the results the impact of the response of the portal imager. And as you can see, all results give or take 2% are good for these bands. The first one, with the maximum gantry speed, is a bit problematic. We do not encounter the same problems with the leaf speed tests. Again, with a rotating gantry, here everything is in green. Globally and individually, dose rate severing, the dose rate with MLC speed is quite good for all MLC speeds. As you recall, for our final test, the snooker Q test, our ISO test object is first at the ISO center, then deliberately shifted 10 cm laterally and 5 cm vertically, so that it is no longer at the ISO center. We then have a sequence for the gantry and a sequence for the leaves at maximum speed, and we will test whether the ball is at the center of the slit, meaning that the gantry as well as the multi-leaf collimator arrived at the correct time. This is tested for various configurations, in particular rotation direction as well as for other sequence for the MLC. There are 4 different tests. We just look at the difference in the position of the center of the ball with the test of the slit. The tolerance is 2 mm. Now that we have finished reviewing the MLCdyn tests with a Varian Linac, I propose we look at the same module with an elector. I will exit and open the second exam of an agility. This will be much briefer, but I would like to show you something interesting. As you recall, here we are looking at picket fence with static gantry and picket fence with rotating gantry. Here we can clearly see the wave caused by the gantry flex, which we must absolutely take into consideration, as here we see static gantry, here rotating gantry. You also note that with elector the minimum slit width is 5 mm, whereas it is 1 mm with Varian. Elector does not accept slits less than 5 mm wide. We will start up the pretest, which consists in detecting in all images the center of the Abacus test object as well as its size, in order to determine the portal imager sagging, gantry flex, and the variation in source imager distance. The Linac presented 1 mm of imager sagging, 2 mm of gantry flex, and a 1 mm variation in SID. The results for this elector are 2 mm of imager sagging, 4 mm of gantry flex, twice as much as for the first example, and especially 10 mm of variation in SID. It is therefore absolutely essential to deduct from the measurements the impact of imager sagging, gantry flex, and the variations in source imager distance. Of course, we can then also control leaf bank sagging. It was 0.6 mm in the Varian example. We have approximately the same result here, 0.6 mm, so we can see that there is sagging. The 2 banks, blue and purple, are parallel, so the same amount of sagging is present. It will impact the slit positions with a rotating gantry, but not the slit width. We will now look at the picket fence test with a static gantry for 4 gantry angles. The tolerance is double for elector machines. 0.4 mm with a static gantry, 0.8 with a rotating gantry. You see all the images with the static gantry, slit position and slit width. everything is okay with a 0.4 mm tolerance. We will now look at the same picket fence test with a rotating gantry, which, as you see, is quite impressive. As you recall, it is not this image that we analyze. We correct the image by applying to the columns of the image the inverse of the improper movement of the portal imager. You can see that we have removed the wave from the image. Positions and width will be measured in this corrected image. As tolerance for Electa is 0.8 mm, the 0.6 mm of leaf bank sagging being within tolerance does not show up in the position results, which are correct, as are the tests of slit width, given that the tests of slit width are not impacted by the improper movements of the portal imager and gantry flex. The test of dose rate and gantry speed servoing shows all results as correct. Within 2%, the dose is constant in all the strips. For all gantry speeds, we see that the dose is maintained. The same is true for the leaf speed and dose rate servoing. The dose is maintained for all speeds. I felt that it was important to show you an example with an Electa Linac as well. Thank you for your time and attention.